So, just a little brief background on the interactions between hormones and their receptors. Hormones only affect tissues with specific receptors. So, hormones do not affect every tissue in the body. They are very specific to tissues that have their specific receptors. And there are a couple things that influence how strongly or how effectively the hormones act. And so the first is the concentration of the hormone. So the greater the concentration of the hormone, the more receptors can be reached and the greater the effect of the hormone can be seen on the tissue. The second factor is the number of receptors on the cell. So the more receptors there are on the cell, the more hormone can interact with those receptors and exert its effect. And then the third factor is the affinity of the receptor for the hormone. So the affinity means how likely that receptor is to attach to the hormone. So we have the concentration of the hormone, the number of receptors, and the affinity of the receptor for the hormone. So those are the three factors that have a significant impact on the strength of the magnitude of the effect of the hormones on the target tissues. Two processes that really regulate how the hormone impacts the tissues. We have downregulation and upregulation. So downregulation is when you have a decrease in the receptor number in response to the hormone concentration. So if you have a high hormone concentration, there's going to be a downregulation in receptor numbers. And so that enables there not to be such a great effect of the hormone. So if we had every receptor and every hormone and all the hormone attaching to that receptor, it might have too strong of an effect. So that downregulation regulates how much impact the hormone has on that tissue. When there needs to be an increase in the impact of the hormone on that tissue, we have what we call an upregulation. So if the concentration of hormone is low, there's going to be an increase in the number of receptors on the cell to help maximize the impact of that low concentration of the hormone. So in order to create this equilibrium or homeostasis, we have the up and down regulation of the receptors in response to hormone levels in order to get the desired effect of the hormone that's going to be most beneficial for the body. So the first hormone I'm going to talk about is growth hormone. So growth hormone is released from the anterior pituitary gland, and its method of action is stimulating release of insulin-like growth factors, so IGFs. IGF-1, so insulin-like growth factor 1, is responsible for muscle growth. So this is important for kids as they're growing, as well as for adults when they're doing things like strength training to help increase the muscle size. Growth hormone is essential for all tissues, so the way it acts is there's an uptake of amino acids and an increase in protein synthesis. So that increased protein synthesis is going to lead to the muscle growth. It's also responsible for long bone growth. So when you were younger, your bones would grow long. We'd have what we call growth plates, the epiphyseal growth plates. And so those are openings at the end of the bone that allow the bone to grow. When growth is complete, those growth plates will close. But during the process of growth, when they're open, that growth hormone is responsible for the elongation of those bones and the eventual growth of the body. Another thing that growth hormone does is it spares plasma glucose. So plasma glucose gets into the muscles through the use of insulin. So insulin's a hormone I'll talk about in a little bit that allows glucose to get into the muscle cell. So the way that the growth hormone works is it keeps that plasma glucose higher by opposing the insulin action. And so that's going to lead to a reduction in how much plasma glucose is taken up by the muscle. This is going to help prevent things like hypoglycemia, where individuals have low blood sugar. It's also going to promote the increase in gluconeogenesis. So I talked about the Cori cycle, where we take lactate and convert it back to glucose in the liver. So growth hormone is going to cause an increase in that process. Growth hormone will also lead to a mobilization of fatty acids from the adipose tissue, which will increase how many fatty acids are being used to produce ATP through aerobic metabolism. And so this figure really shows the different factors that are going to increase growth hormone production. So we see exercise is a stimulant of growth hormone production. Sleep. So when kids are growing, it's very important that they get sufficient sleep because there are big spurts of growth hormone released during that time that kids are sleeping. Stress is going to have an impact on growth hormone release, as well as low plasma glucose. So all these factors are going to have a positive impact or cause the release or cause stimulation from the hypothalamus. So the hypothalamus will release somatostatin and growth hormone releasing hormone. Somatostatin will decrease production of growth hormone, whereas the growth hormone releasing hormone, GHRH, will increase growth hormone production from the anterior pituitary. And so you see the actions of growth hormone. Down here we have blocking glucose entry to adipose cell to favor fat mobilization, increase gluconeogenesis, and an increase in protein synthesis and growth. Growth hormone will also impact the liver and other tissues to release this insulin-like growth factor, and so that insulin-like growth factor will also increase protein synthesis and overall growth of the muscle. Growth hormone can affect performance. So you have an increase in protein synthesis, which increases muscle size as well as long bone growth. Growth hormone has been used to treat conditions in childhood associated with smaller stature, such as dwarfism. It has also been used by athletes to help increase muscle size because their growth plates have closed. You're not seeing long bone growth. And the elderly. So during the process of aging, I talked about muscle mass being lost. So we have that sarcopenia where you're going to have some atrophy, you're going to have some loss of muscle cell number. And so the growth hormone can help the elderly by increasing muscle growth, which will help with their strength as well as their balance and stability. There are adverse effects with growth hormone, with taking growth hormone. So it will decrease the amount of growth hormone being produced naturally in the body when you take it from an outside source. And there's not a lot of strong evidence coming from research that shows big strength gains from growth hormone, from taking growth hormone. So we see minimal strength gains compared to just doing resistance training alone. Also, the results are equivocal, so there's not really strong evidence showing a true benefit of taking growth hormone on that anti-aging effect. So you're still going to see a decrease in muscle mass, you're still going to have muscle loss. It may attenuate some of that loss, but probably not much more than what you would see if an individual was regularly active and doing some sort of strength training. From the posterior pituitary gland, we have the release of the antidiuretic hormone. And so this antidiuretic hormone helps to maintain plasma volume. So plasma volume makes up a portion of your total blood volume. When you decrease plasma volume, so when you're dehydrated, that's going to lead to a number of different factors that are going to impact performance. So when plasma volume is low, that will affect the ability to get oxygen and nutrients to the muscles. It'll have an impact on heart rate, where heart rate's going to be increased. We'll talk more about those effects when we get to the cardiovascular system. And so the way that the antidiuretic hormone works is that it favors reabsorption of water from the kidneys. So as the blood is being filtered through the kidneys, the ADH hormone will lead to an increased reabsorption of that fluid so that you can maintain your plasma volume. What causes the release of ADH is high plasma osmolality. So when you have a higher concentration of the factors within the plasma. So when you have, the plasma becomes more concentrated because you start losing fluid. So when you have a greater concentration of the elements within the plasma as well as low plasma volume, that's going to stimulate the release of ADH. And you usually have that occurring because of sweating, and the individual is not replacing water or fluids during their exercise. Usually when an individual is exercising, once they get above that moderate intensity activity into the vigorous intensity zone, that's when you're going to see an increase in ADH production to help maintain the plasma volume during that higher intensity activity. So here we see changes in plasma volume or plasma antidiuretic hormone during exercise. So here's the percent change in ADH. Here's your percent VO2 max. So it remains relatively stable until about 60% of VO2 max. Then we see an increase. As you get closer to your VO2 max, so 100%, you see that plasma ADH having about a 600 to 700% increase in how much is being produced during that time. So that the ADH will be beneficial for individuals doing activity that's higher intensity as well as longer duration, because it's going to help preserve that plasma volume, which will help to lead to a better performance. When you see individuals getting dehydrated and losing a lot of that plasma volume, that is going to cause some issues that will lead to a decrease in performance. When we cover the cardiovascular system, I'll go through some of those mechanisms that lead to a decreased performance as a result of a lower plasma volume. The adrenal medulla is going to secrete different catecholamines, specifically epinephrine and norepinephrine. So I've talked about these hormones before. Part of the sympathetic nervous system, cause a more stimulatory action within the body. These are very fast-acting hormones, and they're part of that fight or flight response. So when you are doing high-intensity activity or when there's some sort of stimulus or stress that causes a reaction. So big increase in these hormones is going to have that stimulatory effect on different systems within the body. So the epinephrine and norepinephrine are going to bind to what we call adrenergic receptors. So there are alpha and beta adrenergic receptors, and the effect depends on the hormone as well as the receptor type. And so in the next slide, I will show you different receptor types and the effects of the hormone on those receptor types. So as I said, these are fast-acting hormones. To kind of go along what we talked about the last time with substrate utilization during exercise, the epinephrine and norepinephrine are also going to help maintain blood glucose during exercise. So similar to what we saw with the growth hormone. And the way they do this is through mobilization of muscle glycogen. So the muscles are going to use their own glycogen in order to create ATP. You're going to have an increase in liver glucose mobilization. So we talked about the gluconeogenesis, and then you have those new glucose being created, pushed out into the blood. You're also going to have an increase in free fatty acid mobilization, and the epinephrine and norepinephrine will interfere with glucose uptake, so they'll counteract that insulin action at the muscle to reduce how much glucose is being taken from the plasma into the muscle. So plasma epinephrine and norepinephrine are going to be increased during exercise, and the amount of the increase is dependent on the intensity of the activity. The higher the intensity of the activity, the greater the increase of epinephrine and norepinephrine. With increases in these hormones being released, you will see an increase in heart rate as well as an increase in blood pressure during exercise as a result of the action of these hormones. As a training effect, you do see a decrease in how much epinephrine and norepinephrine are released after that training. So during exercise, individuals who are trained as a natural progression through their training, if an individual trains at the same intensity every day, they become more economical. Their body's better at adapting to that activity. So they tend to have lower heart rates, lower blood pressure, lower oxygen consumption. And part of that decrease in all these physiological variables is due to the decrease in the plasma epinephrine and norepinephrine. So because you don't need the heart to beat as quickly, or you don't need to use as much oxygen to do that activity, it decreases the action of those hormones. So here we have the different receptors. So we have 3 beta receptors, 2 alpha receptors. And so I'll just go through each receptor individually. And so with the beta 1 receptor, epinephrine, norepinephrine are going to have an equal effect. And so really what I want you to know is the effect of epinephrine, norepinephrine, and then the effect on the tissues. So with beta 1 receptors, epinephrine, norepinephrine, equal impact. They're going to lead to an increase in heart rate, an increase in glycogenolysis, and an increase in lipolysis. So increase in the mobilization of free fatty acids, increase in how much glycogen is being broken down in the muscle, and your heart rate's going to increase. The beta 2 receptors, you're going to see epinephrine having a greater impact compared to norepinephrine. And so that's going to lead to bronchodilation, so opening of the bronchi and the bronchioles in order to allow more air to pass through, so increase ventilation. And you'll also see an increase in vasodilation, where those blood vessels will open up to allow more blood flow to get through certain areas. And so that's going to help allow more oxygen and more nutrients to get to different tissues when you have that vasodilation. Beta 3, the norepinephrine, is going to have a greater effect than the epinephrine. And so with beta 3, the biggest impact is going to be on increase in lipolysis, which will lead to increased free fatty acid mobilization. The 2 alpha receptors, the epinephrine is going to have a greater impact than the norepinephrine. So with alpha 1, you will see an increase in vasoconstriction. And you will also see an increase in the phosphodiesterase, which will lead to an increase in metabolism, so increasing the metabolic rate. The vasoconstriction will be important because during exercise, we really want blood flow to go to the working muscles and tissues that need it. So you will have some vasoconstriction to tissues that really aren't being used during exercise. Alpha 2 is going to oppose the actions of the beta 1 and beta 2 receptors. So it's going to help to keep heart rate from going up too high, as well as it'll cause a decrease in glycogenolysis, decrease in vasodilation and bronchodilation. And then finally, it will lead to a decrease in insulin secretion, because insulin is going to be used to lead to more glucose being taken up by the muscle. So it's going to decrease that secretion to help preserve the plasma glucose during exercise. Cortisol, another hormone responsible for helping to maintain plasma glucose. So it's going to promote protein breakdown, which will lead to gluconeogenesis. So some of the amino acids can go through the process of gluconeogenesis in order to make new glucose. You're going to have an increase in free fatty acid mobilization. Glucose synthesis will increase, and it will block the uptake of glucose into cells and promote the use of free fatty acids. Cortisol is stimulated by stress as well as ACTH, and that's part of the general adaptation syndrome. You also have cortisol being released during exercise. So all of these hormones that I talked about, I really talked about in terms of helping to maintain the substrates or impact the substrates that we use during exercise. And so two of the major hormones responsible for the homeostasis or balance of blood glucose during exercise is going to be the insulin and glucagon. So in terms of plasma glucose maintenance, there are going to be 4 different ways that we achieve that. Mobilization of glucose from the liver glycogen, so that's going to produce or allow more glucose to enter the plasma. You're going to have mobilization of free fatty acids, which is going to spare the use of blood glucose. You'll have gluconeogenesis, so the creation of new glucose in the liver via the Cori cycle. So amino acids, lactic acid, glycerol, responsible for that. You'll see blocking the entry of glucose into cells, and that's going to force the muscles to use free fatty acids as a primary fuel. And so all of these factors are controlled by hormones. Some are more slow acting and some are more fast acting. Cortisol and growth hormone are going to be the more slow acting hormone activities. Fast acting epinephrine, norepinephrine, and I'm going to talk about insulin and glucagon in the next few slides. So the fast acting hormones, insulin and glucagon. Insulin's responsible for the increase of glucose through the muscle and free fatty acids. When you have an increase in insulin concentration, that leads to more glucose being taken up by the muscle. During exercise, we see a decrease in insulin response, which seems kind of counterintuitive if we want to get some of this blood glucose into the muscle. You do see higher glucose or higher insulin production or release after a meal. During exercise, we actually can increase blood glucose uptake by the muscle without the use of insulin. So there are receptors that appear on the muscle surface called GLUT4 receptors. So these GLUT4 receptors allow the glucose to be taken into the muscle without the use of insulin. This is one of the reasons why exercise is so important for individuals who have diabetes, where they have a decreased insulin production or they don't release insulin, because exercise will actually lead to the surfacing of those GLUT4 receptors and help get glucose into the muscle cell without the use of insulin. You will see decreased insulin response following training because the individuals tend to use less glucose in order to do their activities. Glucagon is going to mobilize glucose and free fatty acids. You will see an increase in glucagon during exercise, and again, you will see a decrease in that response following training. So the insulin and glucagon secretion are being influenced by the catecholamine, so the epinephrine, norepinephrine. So in this figure, you see the influences of both insulin and glucagon. So in the top part, we have insulin, and that's going to impact the adipose tissue, muscle tissue, and liver. The adipose tissue, it's going to lead to plasma glucose being taken up and being converted to triglycerides. At the muscle, the plasma glucose is going to be taken up by the muscle and used as the primary substrate in glycolysis to create ATP. So here's going to be that process. Also, the glucose is going to help to increase storage of muscle glycogen. Plasma glucose on the liver, so plasma glucose being taken up by the liver and converted to glycogen to be stored by the liver, so that when it needs to break down later, it can to release glucose into the blood. Here's your glucagon. When you have an increase in glucagon, the impact it has on the adipose tissue is that the triglycerides will be broken down, and you have an increase in free fatty acid plasma concentration. At the liver, the amino acids and glycerol will be converted to new glucose through gluconeogenesis to increase plasma glucose, and glycogen will be broken down to glucose. That glucose will be released into the blood to increase the plasma glucose. So insulin is going to lead to a decrease in the plasma glucose, and so make sure you know what happens at each tissue. Glucagon has the opposite effect, where it leads to an increase in plasma glucose. So just to summarize how all these hormones impact changes in, or the changes in the concentration, we see epinephrine, norepinephrine, growth hormone, cortisol, and glycogen. All of these hormones are going to increase during exercise. So as you increase VO2, you have a pretty steady response until we get to the higher intensity activities, and you start seeing an increase during this graded exercise. Insulin, there's going to be a drop because we need to spare plasma glucose, and also the muscle can take up glucose without the use of insulin. So that's going to be your incremental or graded exercise, where you go by increases in intensity. The second slide shows hormone responses to prolonged exercise. So exercising at the same intensity for a long period of time. As you go through that longer duration activity, usually about 20 minutes in, you start seeing an increase in these hormones being produced to help spare some of that plasma glucose, and then you see a steady drop in the plasma insulin, and that's going to help, again, spare some of that plasma glucose during exercise. So this is a nice slide that summarizes the hormonal responses, as well as the mobilization of different fuels and preservation of different fuels. So make sure you know the hormone. I talked about the glands, where they're released. Glucagon and insulin both released from the pancreas, alpha cells, glucagon and the beta for the insulin. And so during exercise, you'll see epinephrine, norepinephrine, cortisol, growth hormone, and glucagon all increasing, whereas insulin, there is a decrease in that release. And so in terms of action, norepinephrine and epinephrine, so increased muscle and liver breakdown of glycogen, and so that's going to mobilize both your fat and carbohydrate fuels. You'll also have an increase in free fatty acid mobilization, again to help spare that plasma glucose. Cortisol leads to an increase in free fatty acid mobilization as well as an increase in the gluconeogenesis. And so that's going to mobilize the fat fuels as well as help to preserve the plasma glucose. You also will see a decrease in glucose uptake by the muscles. Growth hormone, again, free fatty acid mobilization, increased gluconeogenesis, decrease in glucose uptake, and so that's again going to mobilize the fatty acid and preserve the blood glucose. Glucagon, increase free fatty acid mobilization, increase the breakdown of glycogen, as well as decrease glucose uptake, again making those free fatty acids more available and to help preserve the blood glucose. And then your insulin, you're going to have an increase in glucose, amino acid, and free fatty acid uptake into the tissues. So that's moving those substrates from the plasma into the muscle. And so that's going to help with fuel storage as well as, if necessary, to lower blood glucose. So make sure you understand how each of these hormones act, so where they're coming from, what impacts their release, as well as how they help in terms of fuel utilization, substrate utilization, and this should all sort of make sense based on what I talked about in the last set of lectures with the exercise metabolism. That's all I have for now. So make sure you go through this material. Again, just a brief introduction to hormones and how some of those hormones are going to impact metabolism and fuel utilization during different types of exercise.